I'd like to go over the is anagram question, which is a popular beginner Leetcode problem. And essentially what it does is it begins by assuming that you have two strings. And essentially the idea here is you want to judge whether or not both of these strings are anagrams of each other. And so the idea behind being an anagram of another string is whether or not you have strings of the characters which are of the same frequency. So the idea here is whether or not you can rearrange one string in such a manner that you get back the other or vice versa. So here we have a string for car, and here we have a string for RCA. I can rearrange the string, which I've called T. I can rearrange it such that it spells car, right? And I can even rearrange S such that it spells RCA. And therefore, both of these are anagrams of each other. Of course, we're ignoring the possibility of uppercase letters. I think that may have a different implementation, but this is a valid approach for judging whether two strings are anagrams of each other in the event we have all lowercase inputs. Nonetheless, the basic idea here is that you receive both of these strings as parameters in a function or method called is anagram. And you begin by judging whether or not their lengths are the same. If they aren't of the same length, then you have one character in excess, and therefore you can rearrange them as much as you want. You'll always be off by one character, and so therefore, if they're of different lengths, then they cannot be rearranged such that they're exactly the same, and therefore you return false in that event. Here we begin by establishing an array called counts. And in Java, at least, if you declare an array in this manner, you instantiate the elements with zeros. So all I've done here is I've declared an array of 26, which means I now have an array that consists of 26 zeros. The motivation behind having this array is simple. We would essentially want to allow each element to essentially represent a particular amount of times that a particular character has sort of revealed itself through the algorithm. And so if we see that a character is present, we go to its corresponding place in the alphabet and we add one to it. And so the idea here is that, okay, you have 26 letters. If I come across a C, I'm going to increment the third index by 1. If I come across a D, I'll increment the fourth index by 1. If I come across an A, I'll increment the first index by 1, right? And we'll get more into about what incrementing by 1 actually does for us. But that's essentially the idea. We have 26 zeros, and we allow each letter to have its own slot, sort of. And every time we see that letter in S, we increment by 1. And every time we see it in T, we go to that same position in the array, count S, and we decrement it by 1. So if we've seen it in S, we add 1 to it. And if we've seen it in T, then we go to the same position where we added 1, and then we pull it down we decrement it by 1. So if I can basically add 1 and then decrement it by 1, that means that that character was present in both of the strings. If I saw it twice, I'll add twice to it. I'll decrement by twice, and so it balances out. I'm left at 0. And so if I can do this, the book's balanced. I've seen it twice in the first in the first string. I've seen it twice in the second string because I know it's 0. As much as I added, I subtracted. It's a way of keeping count. And that means if I can do that, and if I can keep doing that, and then at the very end, if my counts array has all zeros, then I'd have known that I saw each character in S the same amount as I saw in T, right? So that's the idea. And now how do we accomplish this? So we establish a for loop, and we can quite literally choose the length of any array, because at this point we know that they are of the same length. And we essentially begin by, so we say, okay, counts of, see, this is our next goal is to be able to do this thing where every time I see an A, I only increment the first index, or every time I see a C, I only increment the third, so that I replicate the alphabet. How do I do that? And the idea is you use something called ASCII values. So when you essentially subtract characters, you're actually subtracting their ASCII values. And essentially the idea here is suppose I use s.char@, and by the way, char@ returns a character at a particular index. So if I say, okay, the character at 0 or the character at 1, it will give me that character. So that's char@. It's a shortened version of that phrase. But nonetheless, suppose I had a C here, right? So then I do C minus A. So what's the ASCII value for C? It's 99. So 99 minus 97, I get 2. And then that's my index for C, 0, 1, 2, which is the third place in the array. And therefore, I have now attributed C to being, to essentially possessing the third slot in the array. Suppose I had A, right? Suppose I did A minus A, then I'm essentially doing an ASCII value of 97 minus 97, which would essentially give me 0, which I want. I want A to have the 0th index in the array, such that A is the first element, or possesses the position of the first element in the array. Or let's suppose it was, D, right? So I do D minus A. If I come across D, I do D minus A. That gives me the third index, which is the 4th position in the array, which corresponds to being the 4th alphabet in the alphabet. So that's essentially what this does, and then it just adds 1 to it. And eventually, throughout the life of this for loop, it will eventually come across the same letter if it exists in the other string. And then it'll pull that value down. And when it pulls that value down, it should all balance to 0. The same amount of times I've incremented should be equivalent to the same amount of times that I decrement. And so it should all balance to 0 if we have an anagram such that the amount of letters in one string is equivalent to the amount of letters in the other. Let's see a debugging of this. So we begin by establishing both of the strings, and then we essentially jump into is anagram, and we essentially judge whether or not the lengths are the same, which they are. And then we establish an array with all these zeros, and we can basically choose any length. And essentially here we say, okay, well, s.char@ of I. Now, what is I? I is 0. So we're doing s.char@ of 0, which gives us the character at the 0th index for the string s, which is C. So we're doing C minus A, which gives us 3 in ASCII, or 2 in ASCII. So 0, 1, 2. So C belongs. It doesn't necessarily belong here. It essentially, if we increment, it increments the 3rd position, which corresponds to where it resides in the alphabet. And so, if we increment this here, which we will, you can see there's a 1. Now, we're not going to immediately decrement where C was, because we'll eventually decrement when we get here. But we're doing this sort of in tandem with other letters as well. So you can see now what we're doing is we're subtracting here. We're decrementing R. So where is R stored in the alphabet? Wherever that is, it will decrement that value. So when we step into it, it decremented where R is stored in the alphabet. And if eventually the R is in S as well, it's going to add 1 to it and it'll balance to 0, right? So here we'll go again. What do we have? We have I of 1. And so s dot caret of 1 is the character in S at the first index, which is the second letter, which is A. And so we essentially increment the position for A. And here on this line, what we're doing is we're essentially you have I is 1. So now we're looking at t dot caret of 1. So that's the first, that's the character that resides at, the first index, which is actually not the first index. In fact, it's the second letter, which is C. Now we've already added 1 to C before. So this essentially ensures we decrement that down, and that where C was previously stored is now 0. And so, we do this again. So we have now I is 2. So s dot caret of 2, which is the character at, index 2, 0, 1, 2, which is R. Remember, we had -1 here for R. Now we're going to kick it up by 1. And so as you can see here, it now balances to 0. And so we do this again. That essentially ends that process. And then this for loop basically judges whether or not each and every single element within counts is 0. If it is, if at all I is not 0, we return false. Otherwise, if we would have been able to go through the entire array counts without returning false, then it must be the case that it was true, and therefore we return true. And so that's essentially is anagram.